Well, welcome to this online revision session for AQA M2, in which we'll be looking at the January 2011 question 7 on elastic potential energy. Right, in the first part of this question, we're just told an elastic string has a natural length L and a modulus of elasticity lambda, and the string is stretched from L to L plus E, so in other words L is the extension. Got to show by integration that the work done is given by lambda E squared over 2L. Well, we know that the tension is given by lambda E over L, which is the extension at any point. So we need to consider then what happens if we got something of natural length L and we extend it a distance x, and so the initial extension is 0 and we extend it to a point where x is equal to E. We have to work out the work done as we stretch the string from an extension of 0 to an extension of E. And to work out that work done, we will need to do an integration, since the force is varying, because as the string gets more stretched the tension increases. And so to calculate the work done we need to integrate the tension over that distance from 0 to E. And so we are integrating from 0 up to E lambda x over L dx. So if that's the case, we know as we integrate this, differential, or the integral of x is x squared over 2, so that gives us 2L on the bottom here, and we've got to evaluate that between 0 and E, and so when we substitute in, that will give us lambda E squared over L over 2L, so apologies, and then it would be minus lambda 0 squared over 2L, which obviously is 0, and so we get our result. There's 3 marks for that, stating that we know what the tension is for the extension. We'll get its key, and then using that in the integral. So this is a key point at which we will get a mark for our method. We get a mark then for correctly integrating that function, and then a mark for evaluating that integral with the limits that are required. Right. Part 2 of the question. It says we've got a mass of 4 kilograms hanging on the end of a light string, natural length 2 meters, modulus of elasticity 196 newtons, and a second block is attached to it of mass 3 kilograms, so in other words we've got 7 kilograms hanging on the end. We've got to find the tension in the string. So we know that the tension is acting that way. We've got this mass of 7, that's the 2 blocks together, and so we've got the weight acting downwards, which will be equal to 7g. To calculate the tension in the string we use lambda times the extension over its natural length, and so we know that 7g must equal lambda, which is 196, times the extension over the natural length, which is 2 meters. And so rearranging that gives us the extension being equal to 14g over 196. And if we calculate that, we will end up with an answer of 0.7. Again, 3 marks, so a method mark for realising how to calculate the tension. So that's 1 mark at that point. For obtaining this expression for x, be a mark, and then an accuracy mark for obtaining the 0.7. Okay. Part 2 of the question then says the 3 kilogram block becomes detached, so all we now have is the 4 kilogram block on the end, and having removed the 3 kilogram block, obviously the 4 kilogram block will now begin to accelerate upwards, and we've got to find the tension in the string when the 4 kilogram block next comes to rest. So what do we have? Well, we have that the string had its natural length of 2 meters. We then, the point at which we released it, we had an extension of 0.7 at this point here. And then at some point, as the motion continues upwards, there will be a point at which the block will come to rest. So let's suppose the position at which it comes to rest is at this point, and we'll call that distance there x. Okay, remembering the 0.7 runs from here to here. And we'll call this starting point A, and we'll call the point at which it comes to rest B on our diagram. Okay, so this method then will be to involve energies. So if we look at A, we can say that the gravitational potential energy at A is 0. Okay, we can choose that as our 0 level. Okay, so that's the GPE. Be 0. We know that it starts from rest, so its kinetic energy is going to be 0. And then there is elastic potential energy, which we know is given by given by lambda E squared over 2L. So it's going to be lambda, which is 196. The extension is 0.7. So we must remember to square that over 2 times L, which is also 2. Similarly, at B, we will have a GPE, which is going to be equal to mgh, so the mass is 4 g, and h, the height to which it will rise, will be 0.7 minus x. The kinetic energy, since it's now stopped, is also going to be 0, and the elastic potential energy will be 196, and an extension that we don't know, which we called x, so that will be squared over again 2L. Okay, right, so we've analysed the energies, so now we can say by conservation of energy, make a little note of that, we know that the energies at A must equal the energies at B. So what have we got? Well, we've got 196 over 4, which cancels down to 49 x squared, plus the 4g times 0.7 minus x must equal the energies at A, which again are going to be 49 times the 0.7 squared. That's going to be 49 times, well, 0.7 squared is 0.49. Okay, if we now rearrange this, we will get, if we divide through by that 49, is that a good idea or not? Yeah, I think it is, because 4 times the G, 4 times 9.8 is, yeah, and of course G is 9.8, and 9.8 goes into 49 5 times, so we get 5x squared. Yeah, eventually thought it through and sorted it out there. Then obviously this G will now cancel, and so you get 4 times the 0.7, which is 2.8, minus 4x, and then dividing this we get 5 times the 0.49, and that's got to be subtracted, and 5 times 0.49 will be 2.45. And that must equal 0. Okay, so what do we now have? Well, we got the 2.8 minus the 2.45 gives us 0.35. So if we multiply that by 20, that will give us 20 x squared. No, sorry, 100, 5 times 20, 100x squared minus 80x plus 7 equals 0. Right. Well, you could either now try factorising it or use the formula. As it turns out, this will actually factorise, because to get the 7 is 1 and times 7. So if we put 10x here and 10x in here, that will make 100x squared. And then if we put a negative 7 in one of these and negative 1 in the other one, that will give us the 80x. So that gives us two possible answers. Either x equals 0.1 and the other answer, not surprisingly, is 0.7, because that's the point at which we started. So the one we want is the 0.7. Not this one. So we need to be careful to just state the one single value that we require. Right, well that gave us 6 marks. Bit of a fiddle around in the middle there. Analysing our energies correctly and getting to the point where we've used the conservation of momentum, we'll get a method mark and 2 accuracy marks. For getting all 3 parts correct, we'll get both of them. If you only get 2 parts correct, you'll only get 1 of them. So then reducing it to an appropriate quadratic, you'll get a method mark, and then for either factorising it or using the formula, you'll get a mark and then a mark for the correct answer, pulling out the 0.1 as being the correct answer. Okay. Sorry, before we move on, we've got one last part to do, part 3. It says find the extension when the speed of the block is a maximum. Now, what is true? Maximum speed means the forces are in equilibrium, which means that the tension in the string must be equal to the weight hanging on the string. So at some point the tension will be given by lambda x over L, and that must equal the tension must equal the weight, which is mg. So we know that m is 4, so that gives us 4g. This is 196 x over 2. And so from that we just need to rearrange it and calculate what x is equal to, and the answer we will get is, I believe, 0.4. So that last part is quite straightforward, as long as you realise that for the maximum speed the tension must be equal to the weight, because the forces are in equilibrium, there's no acceleration at that point, so tension equals the weight, and then away we go. So the method there, 1 for realising the tension is equal to the weight, and then an accuracy mark for substituting in the correct values into the expression, and then a mark for then obtaining the correct solution or value for x. Well, hopefully you found that solution helpful. For more assistance with your maths revision, please go to the Further Maths Support Programme website.